In this video, I'm going to be going through the concepts of Pythagoras' theorem, trigonometry, and we're going to talk about different kinds of vectors. Specifically, we're going to talk about force vectors. We're going to talk about concurrent forces, non-concurrent forces, resultants, and equilibriums. So, the first thing I want to do is I want to get some key concepts I think it's important to understand. Right? So the key thing that you need to understand is, well, we need to know what trigonometry. We'll start with Pythagoras' theorem and work up to trigonometry. Now, I first went through this with my daughter, who she just started year 7. I was able to explain this to her in a couple of nights. The reality is most people need some amount of time to really internalize trigonometry before it's intuitive and something that they're comfortable with. You guys have hopefully had 2 or 3 years of doing trigonometry, so you should be fairly comfortable with trigonometry. If you're not, this is the thing you need to learn before we go on. This is the sort of thing where you want to go into Khan Academy or Maths Online and you really want to try and understand your trigonometry. What I'm going to start off with is if I have any just generic triangle that has a right angle. Actually, I'll do the classic.
Very full plot.
That's exactly what I'm going to do. Okay, so if I have a triangle that is 3, 4, we can use Pythagoras' theorem to figure out how to do this last side. Okay, so how do we do that? Well, the rule is if we label these, I'm going to call this A and B, and this side here we're going to call C. And the rule is that C squared equals A squared plus B squared. So if we apply this rule here, so we know that C squared equals A, which is 4 squared, plus 3 squared. Right, what we can say here, and how a lot of people display this, how they represent it, is they say that the area, without too much looking, if you go onto the internet and you look for Pythagoras' theorem with water, you can see wheels where what they'll do is they'll fill up a closed area that's on a wheel, and what will happen is you'll see that the area of C squared, the amount of water it takes to fill C squared, is equal to the same amount of water that it takes to fill 3 squared plus 4 squared. Well, we can look at that from maths. We can see that, in this case, 4 squared is 16, plus 3 squared is 9. That gives us 25. 25 happens to be 5 squared. So we can say that C equals the square root of 25. So C equals 5. Okay, so most people are pretty comfortable with that. Most people then also know that we can use this same thing to say that if we need to find A, for example, we can say that A squared equals what? C squared?
C squared minus B squared.
Minus B squared, exactly right. So in that case, we can say that, well, if we now know that C equals 5, we can say that 5 squared minus 3 squared equals 25 minus 9 equals 16 equals A squared. Therefore, A equals 16 squared and A equals 4. So if we understand that, well, let's now apply that to this specific triangle. So this is a 60-30 triangle. Anyone who's bought set squares will recognize that these two angles are the two angles we use in set squares. And that's for good reason. That's because they're very commonly used. Okay, so let's start off with this triangle here. This triangle has 60, 60, 60 degrees. I was going to try and do degrees in blue. You know what we're going to do? Hopefully you hit the forward button to skip that if you're watching this on a video. Okay, what do we know about a triangle that has 60, 60, 60 degrees?
It's equilateral.
Equilateral. So that means that if this is 100, what would these sides be? 100. Excellent. Equilateral means that all sides are equal. Right? And an equilateral triangle. We know this because the angle sum of a triangle is 180 degrees. I proved that an angle sum of a triangle is 180 degrees to my youngest daughter by drawing a triangle. Doesn't matter what triangle you draw. I don't know if you've learnt this in maths, but if you just cut it if we just tear it, right, and I have this as, we'll call this part A, this part B, and this part C, what you can do is then you can actually take that angle, in that case, part B looks pretty close to 90 degrees, and part C is going to be that size angle. You can actually rearrange these things here. You can say, well, that's B, this angle here is going to be C, and that angle there is going to be A, and you can actually fit them together to prove that the angle of some of the triangles is 180 degrees. You can also use a protractor, right? A little bit less elegant solution, but you can use a protractor. Okay, so what we have here is we've got this triangle. Now, what I want to do is I'm going to take this equilateral triangle, which we know has 180 degrees divided by 3, or 60 degrees, and then I'm going to cut it in half. When I cut it in half, what do I get?
Are you drawing a line from the top to the bottom?
Yeah.
And you get a right angle.
Excellent, that's exactly right. So I get a right angle. So what's this angle now here? It's half of 60.
30 degrees.
30 degrees, exactly right. Okay, what is this size? It was 100 degrees, we cut it in half. 50. Okay, so can we calculate what this size might be?
Yes.
How?
They're exact ratios.
Could be 50
Yeah.
squared plus.
Okay, so I want to use a simpler number just to start off, right? Just to start off with. We're going to draw the same triangle up again, but we're going to use a simpler value just to start off. We don't really care about the angles so much at this point. Would it be fair if I said that's 2 and that's 1? Are we okay with that? Yeah, that's fair. So that's the same ratio. 100 is 2 times 50. Now, in this case here, what would the Pythagoras be?
Root 3.
Root 3. Okay, help me get there. So,
squared plus 1.
so it's the hypotenuse squared minus the other square. So we're going to say this side here, we'll call it C. Well, actually, that's a bad example. We'll call it B. B equals C squared minus A squared, right? So B equals, in this
2
case,
squared minus 1
the square, well, okay, you know, I don't want to jump that step. Okay, so what have we got? 2 squared minus 1 squared.
Like it needs to be 1.
Okay, so let's make that, so it goes 4 minus 1, because 1 squared is 1, which gives us, so B squared equals 3. Therefore, B equals the square root of 3. What's the square root of 3? It's equal to 1.73 something. Okay, that's fine. Now, the thing is, I'm going to do that again, but what I want to do is I want to halve everything by 1, right? I'm going to halve everything. So I'm going to make this now 1. This, I might lose some people for a second, don't worry, it's going to come back and I'll explain. I'm going to turn that into 1, what would this be? 0.5, or half. And what would this then be?
Root 1.5.
It'd be root 3 over 2, which we said root 3 is 1.73. Okay, so root 3 over 2 is going to be
8.5.
0.866. Okay, now, if I go back to this one here, we can then write, if this is 100% and this is 50%, what will this amount be?
0.8.
Nope. So if this is 100% and this is 50%, this is 0.866, right? What would this be as a percentage?
86%.
86.6%. Okay. Now, you don't have to remember that. If you want to do it using trigonometry, you can. But the point is, here's the first thing I think is really important. Is if you are asked to find that side, what we know for starters is we know that this side has to be smaller than the hypotenuse. The hypotenuse is always the biggest. That's the definition of the hypotenuse. The hypotenuse is always opposite the right angle triangle, and it is always the biggest side. It has 2 properties, right? And I know that it has to be, in this case, it's the medium side, so it has to be a number that's between 50 and 100. Yeah? In this case, it's 86.6 between 50 and 100. It is. And it looks about right. It looks about right. So here's the thing. I found that I was doing a lot of trigonometry in engineering studies, or in engineering generally, with 30 degrees. It's a very, very commonly used angle for calculations. When I went to uni, I did a maths bridging course, and I had a teacher called Carlos Ortega. If you ever see this, Carlos, say hi, give me a like, and contact me in the comments. Anyway, Carlos Ortega was my maths teacher, and he talked about, he was from Colombia, and he said in Colombia that when he was going through school, not everyone could afford a calculator, so that the exams always used exact ratios. So that way you could always give an answer without having to get the calculator. Now I do use a calculator, but I don't want to say that I'm not good at trigonometry, but I know that trigonometry is an area where I sometimes slip up. And for me, it's a lot more useful for me to say, hey, I've got a 30-60-degree triangle. I'm going to know that this is half as big as the hypotenuse. The small side is half as big as the hypotenuse. And this side is 86.6% of the hypotenuse. You will see me use that in a lot of my solutions where you just see, where did that 86.6 come from? And that's because I've used the trigonometry there. I've said that that's 100 sine 60. Yeah, because it's the opposite of 60. Okay, so even there, I had to think about it because I'm not perfect at trigonometry. Okay, that's our first ratio that I have memorized. I've given this a name, right? I have a friend, he's born in 86, his name's Disco. So I call it the Disco number. If you don't know Disco, you could instead call it the Newton number, right? So Newton discovered gravity in, I don't know, something 86, 1686, who knows? Anyway, something 86, that's an alternative you could call it. I'm going to call it the Disco number because that works for me. Right, it seems to be memorable. I have a lot of students who talk about the Disco number by the time they're in year 12. On this side here, let's go through this same process, right? We're going to start with a triangle. This one's a bit easier actually, which is nice. We like things that are easier. Okay, so that's 45 degrees. Okay, in this situation, if I said that this was 1, wrong colour. If I said this was 1, what's this side going to be equal to?
Root 2.
Root 2, how do we get there?
1 squared plus 1 squared.
Okay, so the hypotenuse is 1 squared is 1, plus 1 squared is 1, so 1 plus 1 is 2, so C is going to equal the square root of 2, which we can write C as root 2. So, how big is root 2? Can anyone tell me as a number? So another way we could write that is we could write that as 100, 100, and 141. Yeah, so root 2 is 1.41 something, right? I don't know after that. Okay, the thing is though, normally what we're given is we're usually given the diagonal, and then we're normally given the diagonal, and then we're asked to break it down into the vertical and horizontal components. That's very typical. We're given the diagonal, so it's much easier to say, well, if I know what the diagonal is, I can just multiply by a percentage. So if I want to, now, so someone who's clever who's got a calculator, they're going to tell me, if I have that same triangle, and if I told you it's 100, what will that number be? I can see some typing on a calculator. We've got an answer? Okay, I've done the answer. Whatever you guys get in the calculator, it's either that or you're wrong. That's a big call for me to make that, but this is one time where I'm going to say I'm relatively confident that that number is going to be 70.7, right? Or if you're doing it as a percentage, it's, you know, if you're going to write that as a decimal, you could say if this is 1, that this is 0.707, right? I like to write it as a percentage rather than as a decimal. I just find that easier to work with. But you do you, right? You don't have to use this at all. If you know your trigonometry, don't worry, you'll be fine. Now, at this point, we no longer need the Pythagoras. We've done enough Pythagoras that we can move forward. And we can just leave our known values. Were you all happy that it was 70.7? Did you all come back to that and you're like, oh, that is right?
I think it was 70.9, exactly. Close enough.
If you do 100 divided by root 2, what do you get?
Oh, root 2.
Yeah.
Oh, I didn't do the exact value. Just probably the thing.
1 divided by square root of 2, it's 0.707, yeah, 0.707107. Okay, so nice to be right, especially on camera, if you're planning on putting this on the internet. So 70.7. Okay, so we're now going to talk about, let's assume that you get some other angle. Right? I hate other angles. Other angles, I don't want to talk about this very long. Right? Because at this point, here's the thing. Even though you guys should have all seen trigonometry by this point, a lot of people don't know this about exact ratios yet. Some of you did. Some of you knew straight away it was root 3 and root 2, and good for you. I like this way better. I like memorizing these numbers rather than root numbers because it's a whole lot easier for me to type in 0.866 into a calculator than it is for me to divide something by root 3. It requires fewer button presses. At least that's me. Again, you by all means can do whatever you want here. Okay, so now that we've got these values, what we're going to do is we're going to prove how we can do this using what's called trigonometry. So the first thing you need to know is if you're doing trigonometry is that there's an acronym that everyone uses to remember, which is SOHCAHTOA. Okay, SOHCAHTOA. Now, my daughter asked, why don't they just write down SOH, CA, and TOA on the calculator? I said, that's a really good idea. That would be a great way of referring to these things, but unfortunately it's not the case. So, what we have here is let's start with sine. So what we're saying is that sine theta, the sine of an angle, is equal to the opposite over the hypotenuse. Now, it's important to remember that we write it as sin, but in actual fact it is sine. Later on, when we do telecommunications, we'll learn all about the sine wave, right, which oscillates between 1 and -1 as we go through the angles of the circle. Right? There's some really interesting things where you can see how that can be plotted as a graph. If you go to Wikipedia, you can see some people have some really great ways of explaining what sine is. Then we have something called cosine. And cosine is the same concept, it's just one wave out, half step out of phase. Yeah, I don't know if I got that right. All I know is it started off okay. Looks right out here. Yeah, okay. The point is it's half a step out of phase. It looks exactly like that, except it's half out of phase. So it's not cos, but it's actually written as cosine. And then there's tangent. And tangent, I'm going to say that that's... is that how you spell it? With a G, right? Yeah, tangent. Look, not a maths teacher. Well, not really. I'm going to say, ask your maths teacher about tangent. He'll be very excited, he or she will be very excited to tell you all about these things. What we're going to instead focus on is what we need to know here. Now, what does it mean to say opposite over hypotenuse? Well, I've already talked about a hypotenuse, and I assumed that you knew what I meant when I said that. But maybe you didn't. If I have this triangle here, I'm going to label this as a hypotenuse relative to, that's by definition is the hypotenuse, right? Even without any angles in question here. The hypotenuse is always opposite the right angle. It's also the side of the triangle that is the largest. So this rule only works if you have a 90-degree triangle, a right angle. One of the sides has to be a right angle. If it doesn't, you're going to have to use a different set of rules, and I'll tell you about that, my thoughts on that in a second. Okay. Then we're given an angle. And then we have some other sides. The side that is opposite the angle, guess what we call that?
Opposite.
Oh, 10 points to Gryffindor. Is it Gryffindor? What are we going with?
Gryffindor.
Yeah, good man, good man. I was talking to a teacher, as an English teacher, and I told her that I was a Gryffindor, and I'm not going to say she slammed her hand on the fist, her fist on the table, but she might have, in dramatic fashion. She was a drama teacher, and she said, "Oh yeah, what's the bravest thing you've ever done?" And I thought to myself, well, this conversation is definitely up there, but I then gave some example, and she's like, "Oh, I guess that's okay." Anyway, so she was very defensive of Gryffindor. Neither of my kids identify as Gryffindor for whatever it is. Anyway, for whatever that's worth. So that's the opposite. What about this one here that's next to the angle?
Jason.
Good answer. If the camera didn't pick that up, the kid said Hufflepuff. Okay, so here's what the idea. What we can do here is we can use, once upon a time we didn't have a calculator that had all the values of sine and cos and tan, or sine and cosine and tangent in a calculator. What you had to do is you originally had to look up a book, and that was a big pain. And then some genius came up with a ruler that when you slid it, it gave you the numbers, and that was pretty clever. And then we had calculators. So now these days no one uses a slide rule unless you're doing it for the kicks. Okay. So I've said here that sine of theta equals opposite over the hypotenuse. Now what that means, I will tell you that I did not understand this at least until year 11. And it's entirely possible I did not understand this until the end of year 11. That if you want to find the different sides of your triangle, you have to use different equations. You have to use the algebra. I'm saying this slowly and I'm stressing it because I did not understand this for a very long time. I just sort of put in numbers and hope for the best. And I can see my daughter, who I think is a pretty smart kid, my eldest daughter, right, who's in year 11, and I asked her, we're doing some vectors the other day, and she's like, she just plugged in numbers. And I'm like, you need to write down the SOHCAHTOA thing, right? I know that it seems like a waste, but you need to write it down because you need to figure it out. Otherwise, you're going to make mistakes. And I find that I make mistakes far less often if I use this because I can use my intuition. I can say, oh, that's 80% as big. Yeah? This works much better for me, and if I'm not using a standard value, I always write it this way. Okay. If I want to find the hypotenuse, what I can do, bit of tricky algebra here, you just either you get this or you can go and ask your algebra teacher and he or she will tell you all about it. Pretty amazing, right? What we did was we just swapped those two positions. I'm not going to go through the maths of that, too much maths for me to go into, right? If you want to find the opposite side, well, the opposite side, what I can do is I can multiply the both sides by the hypotenuse, so that this side gets multiplied by hypotenuse, these cross out, and then this side gets a hypotenuse over here. Again, if you don't get a lot, you know what, I'll do it, right? So I'm going to write height, multiplying by the height, right? And that crosses out. Oh, look at that. Okay, so what have I got here? I can say that's the opposite equals the hypotenuse times sine theta. Does that make sense?
Yep.
Now I'm putting a little dot there just to show you that there's a multiplication, right? But generally the idea is we just write it out like that. Now, let's have a look at how that plays out in reality. I'm going to now, goes back here. Okay, let's test this out. If I know that this is 86, I should be able to find the hypotenuse, right? Let's type it in. So we're going to type in here, we're going to say that hypotenuse equals, h equals 86.6 divided by sine. We're going to use this as our angle because we said this is opposite. Yeah, we're saying sine equals to 60. Can you guys type that into the calculator for me? What do you get? Hopefully you'll get a number, and this is where it's important to do your estimation. You've got to think, am I going to get a number that's bigger than my original value? Is this going to be bigger or smaller? That's really important. You think, is my number going to get bigger or smaller? We know the answer, but it's really important when you do trigonometry to think, is my number going to get bigger or smaller? Can someone type it into the calculator already?
99.99.
99.9999, which we're going to say because we just rounded this number off as being pretty close to 100. Good work, well done. I got a hand up, yep.
Doesn't that mean that when you get your length of material, the angle's going to be slightly off? Or
no, it means I use some rounding, but I want to say that if your answer is within 2%, I'm probably going to give it to you correct anyway. Yeah? Okay, because think about this. We're allowed to use gravity as 10. Yeah, if we're allowed to use gravity as 10, an answer is already off by allowable margin of 2%. Okay, let's do this one. If we want to find the opposite side, this is the one we're much more likely to use, right? It's much more likely that we're going to be given a diagonal and then we're going to have to convert things into its components. So if we're given the diagonal and we have to find the vertical and the horizontal, let's look at that. So what we're going to say now is we've got the opposite equals the hypotenuse times sine. So we said our hypotenuse is 100 times sine 60. Now you're allowed to just type that in just to the calculator, just like that. If you just type in 100 sine 60, what do you get?
86.6.
86.6, excellent. Now, here's the thing. Sometimes, my calculator, I always use my phone because I don't have to go into an exam, right? So I downloaded a good calculator app that I'm happy with. I told my daughter to do the same thing. Download an app that you like. That for me, my one looks like this. I honestly don't even know what it's called. It's called FSC Pro. There you go. That's what I use. Yeah, that's as much endorsement as I'm going to give. I'm not writing that on board. It always uses degrees. I never have to worry. Your calculators that you have in front of you, they have this tricky radians button. And occasionally, you get answers in radians. And your answers are totally off. This is where estimating and saying, hey, my answer needs to be smaller than the hypotenuse, but bigger than the other side. Right? It needs to be, 86 needs to be between 100 and 50. If I get an answer of 200, I know it's wrong. If I get an answer of 3, I know it's wrong. Because it can't possibly be that small. Does that make sense? Estimation. How many times have you heard a teacher from year 5 on say you have to use estimation as one of your math strategies? Has everyone here heard that before? I want to see lots of nodding to see that you've heard a teacher say that before, yeah? Great. This is me saying estimation is an important strategy, especially if you're recording a video that you're going to put on the internet, right? So that you don't go way too far before you realize, oh my God, I've made a terrible mistake. Okay. So we figured out how to do this using sine. Well, what we've said that we typically, it's the same process if we're going to use cos. I mean, I'm not going to teach you how to do trigonometry here, so don't get too excited. But for cos, I'm just going to spill out that much. For cosine, cos theta equals, everyone?
Adjacent on hypotenuse.
Adjacent over hypotenuse. And what we're typically going to use, the example that we're most likely to use, is we're mostly likely to say that the adjacent equals hypotenuse cos theta. If you were just going to do one, like if you were just going to be like me, who's like, you know what, I just do one form and that's it. That would be the one I would use. Because what that does is it turns the diagonal into its horizontal component, typically. We are almost always going to measure our angles from the horizontal. That's just how we do things for structures, right? We just tend to measure from the horizontal. So when we're doing things like trusses, right, or beams, we're measuring a structure from the horizontal. We always are going to use those sorts of angles. So be very conscious of that. That's what we're probably going to find. Okay, the last one. I never really use tan, except when I want to find the angle at the end, right? So what I usually am going to do, I will write it down just because completeness, you know, I'd hate for someone, this was the one opportunity they had to learn trigonometry and I stopped and they're like, well, what's tan? What's DOA? I just can't figure it. Maybe you can't figure it out. Anyway, the idea is that tan theta equals opposite over adjacent, right? There you go. So I haven't left anyone in suspense as to what tan is, right? But we don't use it, not very often, not when we're converting diagonals into horizontal and vertical components. Okay. What we are likely to do is at the end of our question, we will have a leftover amount of horizontal and vertical. Let's say I have 3 and 4, right? And at the end, we've figured out what the remaining amount of leftover vertical and horizontal is. And can someone tell me what would our diagonal be that we're going to recreate? 5. Oh, good work. How did you use that?
Pythagorean.
Pythagorean, yeah, okay. So you use Pythagoras, right? A squared plus b squared equals c squared, which we just talked about earlier. But the question, the HSC is also going to have to ask you to tell me what theta is. How are you going to do that? Smarty? No. Tan. So we're going to use this function here. On your calculator, it's probably written like that. On my calculator, it's written like that. Right? It's tan to the -1, or it's the inverse tan function. It's also sometimes called the arctan function, and in Excel, it's a tan. So you might see I write a tan on the board a lot, right? And what I do is what did we say tan was? Tan, the tangent is equal to the opposite over adjacent. Could anyone tell me, could someone type that into the calculator for me?
$36.8.
No, wait, before we continue, he said 36.8, but before we consider, we want to think, what is a reasonable angle? If I told you the answer was 50, would you think that was reasonable? No, because it looks like it's close to 45 degrees. it should be a little bit less than 45 degrees because it's not as tall as it is wide. Yeah? So it's going to be a little bit less than 45 degrees. So if I told you the answer was 50, we'd say it was wrong. And if I told you the answer was 3, we would say it was wrong. The point is, occasionally, I see smart kids write down that the angle is 3 degrees. What they mean to say is it's 3 point something radians, but I didn't ask for the answer in radians, I asked for the answer in degrees. So if you write down 3 radians, yeah, I'll figure it out and then I'll mark it correctly, but I'll be cranky about it. But what did you say it was, 36?
36.86.
Now, 36.86 degrees, your maths teacher might tell you that you need to convert that into degrees, minutes and seconds, but not me, not me. I am so happy to read 36.8 degrees. And to be honest, if you wrote theta equals 37 degrees, I am still going to mark that correct. And I don't know, but I'm pretty sure that the HSC marker is going to mark that as correct as well. Can't say definitively, but I would, right? I would give that as correct. Okay, so we've now understood the basic trigonometry that we need for this course. Now, there are very, very rarely occasions, and I hate to even say this, where we need to use the big guns, the year 10 trigonometry. We have to use the sine rule and the cosine rule. The sine rule looks like this, ready?
A on sine A.
I don't have a 90 degree angle here anymore. I have 100 degrees, and I have 30 degrees, and I've been told this is 10, and they said, calculate for me what this value is A.
You just said that was an isosceles triangle.
Did I?
No, you didn't.
Yeah, okay. A scalene triangle is what we're looking at here. That is not the world's best degree sign I've ever drawn in my life. I'm going to actually try to stick with my convention of using. So 100 degrees and 30 degrees. Okay. How do you solve this? Okay, in this case, we'd say that A over sine A equals B over sine B. Now, here's a little trick for you, right? If you're trying to find a side, if the side is what's unknown, start with it that way. On the other hand, if you're trying to find an angle, reverse it. So you can write sine A over A equals sine B over. Hello!
Hi, JD needs to go down to go get some photos.
Who?
Hey, Jordan.
Okay,
So can I get a drink, please?
Darian. Okay, so A over sine A equals B over sine B. What does that look like in this situation here? I wish I hadn't written that in red, but I have. A equals sine 30 versus B over sine 100. What? Then I'm going to use my algebra, right? I'm going to use my algebra to multiply both sides by sine 30, and that will give me
10 sine 30 and sine 100.
A equals 10 sine 30 divided by sine 100. Okay. Like I said, super rare. But I'm going to then tell you the one great thing, if there is one great thing about this subject. The one great thing about this subject is, if you own a protractor and some paper and a pencil, you're just allowed to draw the triangle. You're not allowed to do that in maths. In maths, you have to be able to figure it out. But in engineering, you can just get a pen, or a pencil ideally, and you can just draw a triangle that has 100 degrees and 30 degrees, and maybe you can't fit 10 millimeters on your page, or 10 millimeters is too small. Maybe you can't fit 100 millimeters on your page, because that's too small. But what you can do is you can draw 100 millimeters. Yeah, you can just scale up your drawing. What you can do is you can write, let's call this newtons, right? For the sake of argument, we're going to put this answer in newtons, or even better, kilonewtons. And what I'll say there is I'll write 10 kilonewtons equals 100 millimeters. And then when I get my answer, when I measure this, I have no idea what this answer is going to be. When I get my answer, let's just say, has anyone figured it out? Okay, so when I get my answer, I can say, well, it's probably going to be, I don't know, let's say I get an answer of 42 millimeters, right? Again, I haven't bothered to figure it out. If I get 42 millimeters, what's my answer going to be? 42 millimeters equals, at that scale, what's it going to be?
It's going to be
4.2 kilonewtons.
yeah.
4.2 kilonewtons. Again, I didn't do any calculation here. I wish we should use the right value, but I just picked those numbers on the fly and I didn't set up for this. Okay. I mentioned when we talked about communication, you can go and buy a thing called a scale, also known as a scale rule. There's two different kinds. There's ones that are just flat, which have numbers on 4 different sides, or you can buy these ones that are triangles and they have different coloured paint on each side. I'm showing it. Oh, I can do better than that.
Sure.
And they have different coloured paint on each side. Usually one side is green, but not always. And so that way, when you look at the ruler, you can tell which side of the ruler you're looking at by the colour paint that's in the middle. Yeah, I recommend those ones. That's what I used when I worked professionally. I had ones that were set to root 2, which was really good for when I was using drawings that had been enlarged using a photocopier. Right, it was like 1:1 to 1. Anyway. Okay, so we've now talked about Pythagoras' theorem, Year 9 trigonometry, and then Year 10 trigonometry. Does anyone remember there is another part of Year 10 trigonometry? What's it called?
C squared equals A squared plus B squared minus 2AB equals
Look at this guy. What was that? Slow down, buddy. Slow down. What was it?
C squared equals A squared plus B squared minus 2AB equals C.
2AB?
Mm-hmm.
Like that?
Capital C.
Capital C. That makes more sense. Because capital C is going to be an angle. Okay. Do you think I knew that? Because you can